All right, so I'm going to speak today a little bit about amphibious architecture in general, and then what I'm doing with amphibious architecture, which is a project that I call the Buoyant Foundation Project. As a way of introducing myself, I am an assistant professor at the School of Architecture at the University of Waterloo in Cambridge, Ontario. So I want to start with this image of New Orleans flooded in Hurricane Katrina, because that is what got me involved in the issue of flood mitigation and flood damage and what we can do to make people safer and give them homes to return to after a flood situation. Just as way of background, I was one of 3 full-time faculty at the LSU Hurricane Center in Baton Rouge when Hurricanes Katrina and Rita hit. And I was there doing research on wind effects on buildings, but by the time I left LSU 2 years later, I was mostly working on flood mitigation. So let me start by defining amphibious architecture. What is it? Well, it's a term that refers to buildings at this stage, mostly small houses, that sit on dry land like an ordinary building, except when a flood happens, they float on top of the water. They go straight up, sit on top of the water as long as it's there, and then come straight back down. And they do this by having a buoyancy system under the house. And buoyancy system just means that it's something that will displace water in order to lift the house and keep it on top of the water. And they also have a vertical guidance system, which is something that only allows the house to go straight up and then straight back down. So it can't go sideways, it can't move anywhere off of its footprint. It just goes straight up and comes straight back down. So we have seen amphibious construction in the Netherlands, quite well advertised since about 2005. And under the radar, almost completely under the radar, there has been amphibious construction in rural Louisiana for close to 40 years. And I'll be showing you some examples of that in a few minutes. And one of the things that I particularly like about this mode of flood mitigation is that it works in synchrony with the natural cycles of flooding. It doesn't try to stop the water. It doesn't try to make the water do anything other than what the water wants to do. And so it allows Mother Nature to do what Mother Nature wants, and we do the adaptation rather than asking Mother Nature to adapt to us. So in that sense, it's a much, much more sustainable solution than what we often use now, such systems as dams and levees and dikes that change the way the water moves. So these are the examples of what they've been doing in the Netherlands. This is in a place called Maasbommel, and it's a lake that serves as a reservoir when there's too much water coming down the river and heading for Rotterdam. They divert the water into this lake, and in order to be able to and hold it in the lake until the flood risk has diminished, and then they gradually let the water out of the lake when the danger is past. And so in order to be able to use the lake year-round but have homes that are safe from flooding, they've developed this system where, let's see, where's my cursor? Can you see my cursor? Yes? Okay, so these are the buoyancy elements underneath this pair of houses. 2 houses share a platform, and in the space between the houses, there are 2 poles, big round steel posts that come up through the platform, and the house, the double house, slides up and down on those poles. And these are big open concrete boxes, concrete caissons, and the water comes up. And when the water gets to about here, then the house starts to float up and sits on top of the water until the water goes away. Let's see. And so here's an example of in Maasbommel on the left, the normal condition, and on the right when there's a flood. And you can see by the change in elevation here, this is the walkway. There's that walkway that's right there. And here it is lifted up and it connects down here because the water has come up to this level and the house is floating. This is another amphibious house, a very recent one in England on the Thames River, designed by Baca Architects in London. And this is a diagram that shows how it works. Basically, it has a double basement, an outer basement that holds back the soil and creates the pocket in which the inner basement sits. The inner basement provides the buoyancy, and when the water comes, it lifts the inner basement of the house and the house with that until the flood recedes. So now I'm going to show you what we have had in Louisiana for the last 40 years. The red area here is Point Capee Parish. And this is the Mississippi River coming down here. And in Point Capee Parish, there is a lake that used to be part of the course of the Mississippi. And the Mississippi River changed its course and left this lake behind. And it's a very popular place for fishing and recreation. And so there are a lot of houses along this lake. The lake is outside of the Mississippi River levee system. And so when the spring floods of the Mississippi River come, the level of the lake goes up and there's a lot of flooding. And this happens sometimes several times a year, but at least once in most years. And just so that you can orient yourselves, Lake Pontchartrain is over here and New Orleans is here, and this is where the Mississippi River runs down and out into the Gulf. So this is what it looks like. These are very simple houses. We call them fishing camps in Louisiana, and they're basically like the house on the beach or the cottage on a lake in Ontario. So the house shown here is kind of a hybrid. It's partly elevated. When the new owner bought the house, he thought that was not sufficient elevation, and he added the buoyancy elements underneath here. And so you can see he was right, and it wasn't much longer before there was a flood and it was floating. The one very, very important point is that these retrofits are not expensive. So this is a do-it-yourself installation. It's not fully engineered, it's not code compliant, and it's not necessarily very pretty, but it works and it's inexpensive. Here's another one of these installations. So you can see Old River, the name of the lake is Old River. So here's Old River back here under normal conditions. And here it is as the flood's coming up. And I like this shot because it shows how the system works. So there's poles in the ground and a sleeve that comes out from underneath the house and goes around it, and that slides up and down. And these are the buoyancy blocks. They're just big blocks of styrofoam. Which you can't do every place because styrofoam will dissolve in the presence of solvents, gasoline products. But this lake is clean, and the people have had no trouble with the unprotected blocks of styrofoam. There are some of these houses that have been functioning reliably, as I said, for 40 years. Here is another one of these, the view that shows this is the amphibious house, and this is the static house with water halfway up. And here's an elevated house, and here's another elevated one, and here's the mailbox. So you can see just about how high the water is. And closer views, so this is under normal conditions. The pavilion in the back that's on the ground, you can see the lake beyond. And over here, the water is up to about this level on the back pavilion. And take a look at this house. You can see it's elevated quite high. That's actually 11 feet of elevation. We call that, the elevation is to the, what we call the BFE, the base flood elevation, which is the level that's specified by FEMA, the Federal Emergency Management Agency. Oh, let me point out one other thing. Let's see. You see the vertical guidance posts here, that they only go this high? Well, these people realized that that wasn't high enough, so they came back and put them in higher. So now you can see the vertical guidance posts go up a whole lot higher. And another thing to point out is that in terms of lateral resistance, these vertical guidance posts are completely inadequate. But as I said, this is do-it-yourself in the backwoods. And fortunately, because of the presence of this building here, that's going to break up any the water coming in with any speed will be diverted around this building, so there won't be a lot of lateral force on this one, we hope. And in the spring of 2011, there was a much larger flood, higher flood than anticipated. So this house is the one in the background in the previous slide. And this is the 11-foot BFE base flood elevation, but the flood came up to 15 feet. So this house was very, very badly damaged, as was this one. So here's the water line on this house when, even though it was up on stilts to the level specified by FEMA, it still sustained this very high level of damage. So here's a shot showing a house with a permanent static elevation, and here's the flood line on this one. So the house was filled with water up to this level, and here's the amphibious house next to it, and this is the water line because it floated up, sat on top of the water, and came back down as the water went away. And here's another one. This is the amphibious. There's the water line on the buoyancy blocks, and here's the water line on this one, extensively damaged. And here's yet another one. This house was not up on stilts, but you can see how high the water line is, and you can imagine the level of damage inside that house. And here's the amphibious one that went up, sat up on top, came back down. And I have to say, compared to the other ones, I'm much happier with the size of these vertical guidance posts. Yes. And this is Buddy Blaylock's house. He's one of the few full-time residents. He lives in this house all year round, and when the flood comes, he goes up with the flood. And so you can see that happening. I should tell you, this photo was, actually I took this photo a couple of years ago. This is a much earlier flood, and you can see that this photo was taken before this other house was built up on stilts next door. And you can see in a flood how high up Buddy's house is floating, because only this much of the posts is showing. So there's quite a lot of flooding, and Buddy is sitting pretty there. And here's another view. So this is the lake in the back that has turned into a much, much larger lake. And the water does the work of protecting the house. The water is lifting the house, and that's conceptually one of the things I very much appreciate about this solution. So what is the Buoyant Foundation Project then? The Buoyant Foundation Project is the work that's the name of the nonprofit organization that I set up as the umbrella research organization for the work that I've been doing for the last 10.5 years on developing retrofitted amphibious systems for existing houses, for places where people are already living somewhere, they have a community, they don't want to be forced to move. And so I took the example of what people have been doing in Old River Landing and fully engineered it and made it code compliant, and also made it more aesthetically appropriate for an urban environment. So the Buoyant Foundation Project is my work, and it is specifically for retrofitting, and it works most easily on a pier and beam house, which means it's a house that's already elevated a little bit off the ground, sitting on masonry piers. There are three basic elements. There are buoyancy blocks underneath the house to provide flotation, and they can be anything that will displace water. They can be blocks of styrofoam, they can be empty barrels, they can be pontoons, they can be pre-manufactured purchased dock floats, anything that will displace water to provide enough buoyancy to lift the house will work for buoyancy blocks. And then, of course, we need some sort of vertical guidance system, and then a little bit more structure to tie everything together and attach the house to the vertical guidance posts. So one thing that's very important to say about buoyant foundations is, as we are designing them now, they are not intended for places where there are waves or where the water has a lot of velocity, where you have high-speed water. I believe those solutions will come in time, and I have, in fact, been working on some, but for the time being, we are not suggesting that this is a good thing for places where there is a lot of lateral movement in the water. So that means we're looking for floodplains, areas that are protected by levees that might overtop, where there are barrier islands, and places where the speed of the water is diminished. So it's important to say that this is not a one-size-fits-all solution. It doesn't work for every situation, but for the situations where it works extremely well. So what are some of the advantages of buoyant foundations? Well, they temporarily elevate the house. They take it up exactly as high as is necessary, but otherwise the house stays close to the ground, so it's not disruptive to the lifestyle. It's also less susceptible to wind damage, because as you move any sort of structure higher above the surface of the earth, the speed of the wind picks up. So you put your house up on stilts, you're going to be more likely to lose your roof than if your house stays close to the ground. Also, because it's a flexible system, it can take soil subsidence and rising sea level in stride. It's a very, very good climate change adaptation strategy, as well as the types of flood mitigation that we've been seeing for decades. The house looks essentially the same as it did before. Very slight change in the appearance. So it preserves traditional architecture. Your neighborhood retains its original character. This is a very, very good solution for historic properties. And the best part of all, it's really cheap compared to permanent static elevation. Generally about 30% of the cost of putting your house up on stilts. And this is because with a retrofit of an older house, you can do what's called grandfathering in the current foundation. You don't have to, just adding the vertical guidance posts that take all of the lateral load, anything that's pushing horizontally on the house, like the force of the flowing water or wind forces. That gets carried by the vertical guidance posts, and so the existing foundation can remain to carry the gravity loads. Whereas with permanent static elevation, the entire gravity load-bearing structure has to be replaced. So in 2007, I built a prototype with my students at LSU, at the LSU Hurricane Center. These slides across the top show developing the platform, and then when that was finished, this was the team of students who had done that. Then we put a temporary flood wall around it. We made a barrier out of corral posts, corral panels, and lined it with plywood, put a swimming pool liner in it, put sand down on that, pumped in the water from the muddy Mississippi, and then ran a series of tests on our installation, tilting it and applying lateral forces to it to test the stability, and it worked just fine. This is a diagram of the final system as it might be applied to a shotgun house in South Louisiana, showing the vertical guidance posts, and now they're designed to telescope out of the ground. They pull out of the ground from the top. There's an outer sleeve and an inner pipe, and the inner pipe pulls out of the top, kind of like the old-fashioned car antenna or the handle on a rolling suitcase, and underneath here you can see the blocks of styrofoam. And then we put a screen around it, both to protect it, to help it visually, but also to make sure that waterborne debris does not settle underneath the house. And so here's our test that we were doing, and we used barrels full of water to simulate the dead load, the weight of the house and roof and walls, the structure itself. And then the sandbags are what we call live load, and that is the equivalent of the people and the contents and the furniture. And we looked at a situation where if most of the live load were along one side, the side of one wall, how much would that tilt the house? So we've got a lot more sandbags piled up here, and we were testing the stability, and it did just fine. So I'm going to show you a little sort of flip card video here, comparing these three situations. So the typical shotgun house, these are long, skinny houses. So this is just the front elevation. So typical shotgun house sitting 3 feet off the ground on piers. What happens if it's elevated to 8 feet, and what if we put in a buoyant foundation with the buoyancy blocks and the vertical guidance posts. So here's the same three situations in a different view, and now we're going to add water. There we go. So which house would you want to live in? The conclusion is, why fight floodwater when you can float on it? So here's this is a type of drawing we call an exploded axonometric, which pulls the house apart and shows what the different components are, including this screen around the bottom to hold out, keep out the waterborne debris. And now I have, this is a real animation, and shows how the components get put together. And I'm afraid my animation isn't working. Ah, there we go. So the house goes up, the vertical guidance post sleeves go in, that's the reinforcement for the existing sill beams, and then the cross beams, and lifting that up so you can see what goes in next. And then these are more transverse supports and bracing to hold the buoyancy blocks. And that's the inner sleeve of the vertical guidance posts going in. There are buoyancy blocks. Now we have the screen around the base. And now we add water. So the screen at the bottom keeps any debris that's tumbling along the bottom of the water, along the ground, from depositing itself under the house. And this is a render of what it might look like on a typical shotgun house in New Orleans. And so I'm going to show you a competition project we did. This is the Farnsworth House, which is a famous modernist house in Illinois, in Plano, Illinois, and it's right on the Fox River. And this is what it usually looks like, and it sits elevated up above the ground. a little bit to allow for the flooding. But there's been a lot more flooding recently than what was anticipated when the house was built. And this happens all too often, and sometimes the water goes even higher and there's a huge amount of damage. And so what could we do? Well, working with my students, they're very good with Photoshop. So here's the ordinary condition, and this is what would be if the house were not able to float and we had an extreme flood. But if it were provided with a buoyant foundation system and that same flood here came, the house could float up like this, and there would not be damage to the house. So here I have another animation for you. So digging the pit and putting in extensions of the existing columns. There's the buoyancy and the structural system over it. Here come the telescopic poles, and the house comes back down and everything gets fastened together, and then the water comes. And it floats up and sits on top of the water, and then when the water goes away, there should be mud on the entrance pavilion. We got the mud on the grass, but not on the entrance pavilion. And this is a render of what it might look, and a little canoeing adventure on the flood. So to finish up, I want to tell you about the first International Conference on Amphibious Architecture, Design, and Engineering, ICADE 2015, that we held last August in Bangkok, Thailand. We had 60 people from 17 different countries, and from all of North America, there were only 3 people there, myself and the 2 people that I brought with me. So we decided that the next ICADE needed to be something to inform North America and try to bring North America up to speed. So we are holding the second ICADE conference, International Conference on Amphibious Architecture, Design, and Engineering in North America at my home university, the University of Waterloo in Ontario. It's about an hour's drive west of Toronto and 2 hours north of Buffalo. And it's going to be the end of June of 2017. And here is the web address, www.icade.org. And I hope to see you all there in Ontario next June. Thank you very much.